So welcome back, everyone. Now we have George speaking about OpenPOWER and Trusted Boot. So enjoy.
All right. Thank you very much, and I appreciate the opportunity to talk a little bit about the work that my team has been doing to improve the security ecosystem for OpenPOWER. I am the IBM Linux Technology Center security development team lead, and I'm a security architect there. And Linux Technology Center, the part that I'm in, has moved under the Power organization. So we are largely, although not exclusively, focused on power systems nowadays. And then with the acquisition of Red Hat, there's another Linux Technology Center over there. So I expect we'll be interacting a lot more with them. Originally, this was proposed as a lightning talk, so I've expanded it, and hopefully I'm giving you more for your money. So with that, I'm going to take you through some background and rationale for this project, some OpenPOWER specific things, some major boot components of OpenPOWER, because you're probably, most of you, not very familiar with OpenPOWER. Hopefully you'll become more familiar since we're opening up the architecture even more. The firmware foundation for Trusted Boot, OS Trusted Boot, Secure Boot, and the firmware and the operating system, the current state of the project, and then, if I have enough time, some extension into the OS and to guests. So standard disclaimer, these are really my views. Whatever I'm presenting here may or may not make it into products. I hope it does, because I want to keep my job, but I have to tell you that there are various trademarks here as well. So a little background, Secure Boot, and by that I mean signed components that are verified at boot time. These are this is a feature that's expected by customers nowadays, and standards are requiring it more and more often. Trusted Boot, which is TCG style measurement and PCR extensions, is useful for assessing system state, and we expected there to be more standards around it by this time, but I expect that might be changing. I see a lot of interest in attestation nowadays. And so we're working towards a comprehensive, secure, and trusted boot solution for OpenPOWER. All Power 9 systems nowadays ship with a TPM and sign firmware, and the firmware exploits the TPM by producing an event log and extending measurements out to the TPM PCRs. However, it currently only extends to the bootloader, and it stops. And that's where my team is focusing, is adding the flexibility to manage different operating system certificates and creating a workable key management. Hopefully, we'll get it on through to the OS and beyond in the relatively near future. I probably don't have to give a lot of rationale here for this, but I mean, we've seen evidence of real world firmware attacks from a number of quarters, and government standards, not just in the US, but worldwide, are beginning to require secure boot and trusted computing instrumentation. So I won't belabor that a lot. It's just recently announced that the OpenPOWER Foundation has moved under the Linux Foundation. So we've opened our ISA and produced a softcore implementation of that that was just demoed. So I'm happy to see not only is now all of our firmware open source, but we're making the actual CPU design information more available. And that can allow you to see everything that's in your system, which is very cool from a security standpoint. It is, however, its own thing. It's not UEFI. It's not anything else. It's got its own design from the ground up, rooted in the older PowerPC work in Power VM and before. We have two distinct security domains with two different key authorities. What we call a firmware security domain that's rooted in hardware. And then that gets handed off to a software security domain where we need to implement this flexible key management so that different operating system kernels can be verified. We have a device tree. We don't have an SMM. We are not planning on any time in the near future implementing a DRTM capability. Our trusted computing is static only at the moment. And most importantly, from a secure boot standpoint, we don't have any reliably lockable storage. So no lockable flash. This was a limitation because the hardware designs didn't initially consider secure boot. So we're still sort of living with this model, but we have a TPM. And the TPM offers us the ability to have a small piece of secureable memory that we can update early in the boot process and lock the door behind us by throwing away the key to that allows us to write it. And this turns out to be the most important thing for our secure boot solution that allows us to actually have one. I won't go into a great bit of detail, but I want to tell you a little bit about the boot components. So we have this small pre-firmware processor called the self-boot engine that does some initialization, passes control off to host boot. All of the routines that are used to verify the earliest code are contained in a one-time programmable ROM. And then we have a CPROM that stores a hash of our firmware keys so that we can actually go update firmware if we have to do key transitions. What we call the PNOR, the processor NOR, is a NOR flash that holds our firmware images and our secure boot certificates. Host boot's really the early stage firmware that does basic initialization of buses and memory. It hands off control to ski boot that does more initialization, and it provides runtime services. So this, you may have heard of Opal, the OpenPOWER abstraction layer. Ski boot's what actually provides Opal. And then ski root is what ski boot hands over control to after it finishes. And it's actually a Linux kernel with an embedded RAM file system that runs pettyboot in its user space. And pettyboot is what's used to kexec the OS kernel finally. So the little gold box there represents what my team is presently working on now. It's higher up in the stack. And everything below it already has a secure and trusted boot capability. So the TCG server spec is kind of, old and ossified, and it largely defers to the PC spec. So we've tried to map the PC client spec and UEFI specs into OpenPOWER in a reasonable way. And we tried to provide reasonable PCR semantics so that attestation makes some amount of sense. We can't do that in all cases. maybe we need architecture-specific standards in the TCG to address these non-PC architectures. In our case, we're using the device tree to locate our TPM and the event log area and pass that along to higher layers. And as I mentioned before, we only have a static root of trust for measurement. The measurement starts with the self-boot engine measuring host boot. Host boot loads another layer called host boot extended, and the host boot extended is actually the first piece of firmware that has the ability to communicate with a TPM. So the TPM measurements are squirreled away until such time as host boot extended can extend those into the TPM. So our CRTM comprises the SBE, the ROM code, and all of host boot. And the CRTM depends on its integrity being verified by secure boot. So the signing and verification of the firmware modules. And then the firmware measurement chain stops when ski boot measures ski root, and that's when we transition to the software domain. So what happens once we get to the petty boot bootloader and ski root? So this init ramfs image contains the petty boot application. It calls kexec file load to load the kernel so that it can pass control over to it, and it uses IMA appraisal to measure the kernel before it passes control over to it. Ski root largely relies on IMA. We're adding some checking in the kernel, for instance, checking loading of keys. But we're essentially already we already have this mechanism available. That's a really nice mechanism in the Linux kernel to measure what's going on in the kernel. So why not take advantage of it? And as I mentioned, we pass things up in the device tree because we have it available to us, and it's reasonably secure. However, the IMA event log is maintained separately from the firmware event log, and so we modified kexec file load to pass the event log up to the next kernel in the purgatory area. And in this way, you can envision an infinite chain of kexec kernels that each extend the IMA event log so that you have a complete log of what IMA's measured through all the kernels that you kexec. And you might envision this being used by not just this, but maybe you want your crash dump kernel measuring stuff. And there are other cases where this might be useful. We thought about like self-encrypting drive secrets, passing them up through the purgatory area as well. Haven't implemented it, but it's a thought. And then of course, when and if we extend this into guests, we need virtual implementations of TPM and signed firmware there. I won't talk a lot about how the firmware is signed, but suffice it to say that it's signed and it's encapsulated in what we call containers, maybe the most overloaded term of the decade. But it actually contains 3 different keys that can allow for different key authorities. We maintain our signing keys in an HSM so that the signing keys can't easily escape. And we keep a hash of the hardware keys in the CPROM. And the firmware can really only be updated by applying a security jumper so that you update the host boot and the CPROM concurrently. So you can actually change it, but we've made it hard to change absent a physical attack. So once again, verification begins with the self-boot engine checking host boot. And the chain really begins in the ROM code that's immutable. So it's a true immutable chunk of code, and it's got all the verification routines in it, and that can't be changed. So hopefully we don't have any bugs in it. I already mentioned you can update it with a security jumper. And then this chain of trust comes to an end. It's key root as well, and that's our the layer that, remember, that's our Linux kernel that executes our bootloader. So what about OS Secure Boot, what we're working on? So we have no central certificate authority in our case. The system owner is the system owner. It's up to the system owner to sign updates. And the system owner could be the administrator, the system owner could be the manufacturer, and it supports flexibility there. This is very much akin to the key hierarchy that you see in EFI. We've used the same variable names, and we've also used the same FE signature list format for tool compatibility. So the idea is that most people, you absolutely must generate your private keys offline and not keep them on the server where you're doing the verification. And most people will probably want to do it on a laptop. So why not reuse the same tools? This is about the only compatibility that we have with EFI, but we thought that this was a useful takeaway out of UEFI. So I mean, you sort of read the diagram that the keys in the higher level verify the public keys updates at the next floor level until we get to the actual kernel verification at the bottom. Probably everyone's pretty familiar with UEFI Secure Boot at this point. We do aim to support scenarios where you sign your own kernel, manufacturer signs the operating system, or we preload a Linux distribution or other operating system. We're only going to have a couple of modes that are similar to UEFI modes. Setup mode, where unauthenticated updates are permitted, and then user mode, where authenticated updates are required to update the key store, and then you have to assert some sort of physical presence to bypass that authentication. And there are a couple of different kinds of physical presence. One is a jumper on the board. Another, in some models, is a special power switch that you hold the power button in for 3 seconds or something like that, and you assert physical presence, and then you can go bypass authentication. So you got to take a physical action. Authenticated updates is generally the scalable way you want to do this. You don't want to have to go around to 1,000 machines in a data center and assert physical presence, but you also don't want people to be able to bypass it easily. So it's a trade-off between convenience and security. We're signing the kernel with the sign file utility that is used to sign kernel modules. We're not using the PECOF format that Intel, Microsoft use. And by appending the signature to the end of the kernel image, we're able to provide backward compatibility. So that's kind of cool. We're just using SHA-256 with RSA 2048 signatures right now, just as they're doing for PECOF. The Linux initramfs is not signed. It's volatile. Most distros regenerate it on installation. This might be a case where we can apply IMA appraisal, which allows you to sign files and verify them. That requires CPIO support for X adders in the Linux kernel. And there is a patch for that going upstream now. So hopefully in the near future, we'll be able to do this in the init.ramfs and extend the chain on up unbroken into the operating system. And our signatures need to be compatible with guests as well, which shouldn't be a problem, but that was certainly a goal. So key management is, as you might imagine, the hard part of this. Since we don't have blockable flash, we store a hash of the key store in a TPM NVRAM index, and we can update that in the ski boot layer here, and then write a random password on it, throw the password away, and write lock it away from the higher layers. So we can do all of our processing and then prevent operating systems and bootloaders from touching it. And this corresponds to scenario 3 in the NIST server BIOS protection guidelines. So we can actually meet that specification with this design as the spec or as the standard currently stands. The updates are placed into an update queue that's stored in pnorm, and because each of them are signed, even if you tamper with them, we can detect that and throw those away, throw an error. And every update requires a reboot. We don't do any of this in line. We don't have an SMM. So it's a simpler model, a little more cumbersome to deal with maybe, but simple is often good for security. So hopefully that applies here. So the ski boot layer verifies the updates using the PK or the KEK public key. And the PK is special in that it has its own NVRAM index. And that's because it controls the mode we're in, and we want to be able to switch modes atomically and not worry about the rest of the key store. Similarly, the key store has its own NVRAM index, and we switch banks after an update, and we want to be able to do that atomically. As I mentioned, we lock this behind us after we do the update on the update cycle. We can race against external changes. Nothing we can do about that in the current design. Hopefully in the future we'll have lockable flash so we can prevent races, but we have to check the key store now against the hash and the TPM before we use this. So we can't prevent someone infinitely denying service right now, and that's something we want to address in a future design along with our hardware colleagues. When the underlying firmware keys change, we invalidate the software keys. And if for some reason you can't update the key store because, say, the machine ownership has changed, and you don't have the private key to go sign an update, then you can assert physical presence with this jumper or power button. So when we verify this, as skiroot boots up, it populates the kernel keyring, the IMA keyring with keys. And then when petty boot is used to select signed kernel, it uses kexec file load, and kexec file load uses IMA to verify the kernel. And we had to patch IMA to add this capability for an appended signature. IMA normally uses extended attributes in the file system to store the signatures. we didn't think it was desirable to have a two-part thing. Extended attributes always seem to cause problems since forever. So it's nice to have the signature appended and have it verified. So other architectures might find this useful too. Everybody's got kexec kernels, so we're hoping that this is a generally useful thing. And so we have an Arch-specific policy right now for PowerPC to go add this kernel policy to verify the kernel for our ski root kernel. So we also need to make UI changes to the petty boot UI. So of course it needs to accept FE signature lists. The PK presence determines the secure boot mode, so it could go read that and report status. Password authentication has been added to petty boot. It previously didn't have password authentication. So now we can control changes that are done through the petty boot UI. You know, this is still a work in progress. We're also adding hardening and lockdown patches to the Linux kernel. There's Matthew Garrett's rather extensive set, and I don't know if he did like 40 iterations or something like that on those. It looks like they're going to finally get to where they're acceptable since it's an LSM now. But there are some of those we can use on Power. Some of them don't make any sense. We don't have ACPI tables, so we don't care about that. We have our own problems, like we have Xmon, a built-in debugger. You may not want to drop into Xmon where you can go twiddle with memory, you know, when you have some sort of error. So that's one of the patches that's proposed. So we know we need to harden this and lock it down. And we also need to restrict the shell further. Right now, you have pretty much unfettered access from the shell. And so we want to use IMA appraisal and SE Linux and minimize the operations that an administrator can do from that. It'd be nice to have everything that you bring in have to be signed. Like there's a RAID setup utility. It should be signed. It shouldn't be some random binary you're downloading. And as I mentioned before, the key generation and signing of updates really needs to be done offline. So we're not providing tools to do that as part of this environment. We don't want to encourage bad practices here. And the administrator can go generate these, and then you can set up a network interface and fetch the updates offline. Not sure how we'll make that easier in the future. I'm not sure that we really should. Current status is that select Power 8 models premiered secure boot, and select models could have TPM cards in Power 8. All Power 9 models ship with a TPM and ship with firmware instrumented to do extensions of PCRs, create an event log, and to verify the firmware. We've been socializing our secure boot solution with OpenPOWER with our Linux distribution partners. Right now, Ubuntu signs the Power kernel with sign file. We anticipate Red Hat is going to do this in the very near future. And that'll give us the ability to verify these, you know, out of the box, much as you do on x86 nowadays. And we anticipate that the OS Secure and Trusted Boot will premiere next year. So we're not done. The chains of trust, the secure boot chain of trust and the trusted boot chain of trust need to go on up into the operating system. And you know, we don't directly control that, but we'll certainly levy features against distros to harden the kernels. And in particular, kexec load needs to be prohibited. Everybody needs to use kexec file load, so you can kexec sign kernels. So even your crashed up kernel should be signed. And as I mentioned, that we need the power and lockdown and hardening patches. IMA appraisal can extend this secure boot chain of trust up into the OS. It's been slow in adoption. It'd be really helpful if distros would lay down the signature metadata when packages are installed. And there are patches upstream to do that, but getting them to do this has been a bit of a chore. And there are things that IMA appraisal does, like slow things down. So people don't necessarily want that if they don't care about security as much as they do about efficiency. Passing the IMA event log should be done so that you have this complete chain of measurements. And we're also thinking about guests. I think in the interest of time, I'll probably skip what we're thinking about guests, because that's really not, that's not fleshed out well. I've got a couple of slides on it. Taking our solution and putting it into the guest would be possible, but problematic. We had nixed that idea. Now we're thinking about it again. So, and then you have the problem with KVM of how you create a complete chain of trust through the hypervisor. IMA can help that. IMA has some blind spots though, so it may not be the way forward there. But it's better than no verification. And DRTM, you know, we certainly see value in DRTM. But in our case, it would require a memory preserving IPL. So Intel and AMD have instructions to do this. We would have to go back through a rather slow IPL process, which would make it painful and I think limit the usefulness of DRTM. So for the moment, we're not really contemplating that. So I'm going to skip over the guests. So, you know, there's certainly good reasons for doing this. And we think that we want to stay out of the way. We want the machine owner to be fully in charge of the machine, however you define the machine owner. Developing secure boot has not been easy. I was not experienced in this area. We come from OS land and we're working on firmware more. So that was challenging. My team has been really good. This is really an update to a series of talks that Eric Richter, Claudio Carvalho, Nina Jane, and others have presented at the Linux Security Summit and Open Source Summit. So it's taken us a while to get here. And having well-tested components hopefully helps us along the way. And we tried to learn from other open source firmware projects and from other secure boot, trusted boot experiences on other architectures. Having fully open source firmware makes life really easy because you can go talk about this stuff, and you as users of the systems can go audit that firmware and see exactly what's running in your systems. So that's pretty cool. And hopefully solving these Arch specific problems can help the whole ART advance. So I've got a couple of references here in case you're interested. I've updated this presentation from what I originally posted, but these references are in that. So questions?
Hey, sorry, I'm not sufficiently familiar with OpenPOWER bring up stages. So at what point do peripherals get DMA to your system?
At what point do I what?
Do peripherals get DMA?
Oh God, that's probably in ski boot.
Okay, can you go back to the
the
slide
boot
with like
sequence?
the yeah. Okay, so the SBE is some immutable thing.
Yeah.
Okay, then in like OTP ROM someplace, then you have. Sorry, I'm just trying to walk through it so that it's clear. Can you go to like 2 slides forward, I think?
Yeah, sure.
Yeah, that one. Yeah.
Okay.
Okay, thank you.
Sure,
Hi.
you're welcome.
Yeah.
Yeah, they're actually like, there's a nifty diagram of like the 24 steps to boot a OpenPOWER system that's available out on the OpenPOWER GitHub. So that this is an abstraction of an abstraction of an abstraction.
So the event log, is the goal to propagate this as far as the boot is linear? Like as long as there's just one chain that's
Yeah.
next, and until the point where you're loading applications that are, and then at that point use IMA or whatever.
IMA, yeah,
onward?
yeah. So this is not updated after we hit the bootloader.
Okay. Is there and then I'm also not sufficiently familiar with the kexec handoff, like what fields there are. So is there a generic like aux data thing, just like blob of this size at this place that you propagate stuff through, or
yeah,
how did you implement that?
We've used what they call the purgatory area. So we preserve that memory across the kexec, and basically the next kernel can go grab it from that area. It has to know to do that. So that's why we need to get patches into distro kernels, so that if you kexec from there, you don't use kexec load. That's prohibited. And then it knows to go grab that event log from the previous kernel, so it can chain onto it. So it's essentially a memory leak across kernels, if you want.
Yeah, sure. And then which of these stages live in some kind of flash versus disk or whatever?
Actually, everything above the SBE lives in flash.
And then, so everything from host boot to petite boot are flash,
Yep.
and then OS kernel is
that's all
okay.
flash. Yeah.
And then if I want to update that, can you go to the key management hierarchy you had?
Yeah, sure.
Okay.
Is that the one you want to?
Maybe. Okay, so there's a per device key in something immutable, and then there's the owner controlled key in flash that's write protected at anything post boot.
It is not write protected. It is stored in this very mutable PNOR flash, and we actually have to go check it against the hash that's stored in this TPM NVRAM index.
Okay.
Which is not ideal. We'd like to just have lockable storage, and I hope that in a future design that we'll have significant sized lockable storage so that we can go do that, and we don't have to do this business with the TPM, because I mean, this is time of check, time of use, right?
Sure.
Kind of stuff. So you don't want to. Fortunately, there's nothing else going on except the BMC at this point. So, but the BMC could go reflash PNOR and prevent you from booting. And there's nothing we can do about that except detect it and say somebody corrupted your PNOR. And that's something you would want to know about, but we can't recover from it in the current design. Hopefully, in the next iteration, we'll have reliably lockable flash, and we can go just store our secrets in there and not have to recheck them against this hash. So it's not ideal, because once again, it wasn't designed with secure boot in mind. You really do want to think about security holistically, and I can tell you that we are thinking about security more holistically now. Spectre Meltdown woke a lot of people up, that you need to think about security. I've actually heard hardware engineers say that security is more important than performance, and I've never in my life heard them say that until Spectre Meltdown. So yeah, I'd say that we're addressing that, but now, yeah, it's kind of ugly to have to do this checking against the hash.
One more question. We still have a few minutes. Right, then. Thank you very much.
Thank you.